In this video, we're going to discuss how row operations affect determinants of matrices. So remember, we have three different kinds of row operations, so we'll talk about each of the three of them in turn. So the first kind of row operation we have is multiplying a row by a scalar. So for example, we might multiply the second row by 5, which I'll denote 5 row 2 goes to row 2. And as we talked about in Module M, we can represent this with matrix multiplication by multiplying by a matrix where we've done the same operation to the identity. So here we've multiplied row 2 by 5. So I've just multiplied row 2 of the identity matrix by 5. If I take any matrix A and multiply Q1 times A, that will multiply the second row of A by 5. Now to think about how this affects the determinant, we want to think about what's going on geometrically here. So we're thinking in terms of transforming, in this case if we're talking about R3, the unit cube, and our basis vectors are going to go to the columns of the new matrix. So our first one is going to go to 1, 0, 0, right where it was before. Our second one's only going to go to 0, 5, 0. So all the way over here. Our third one's going to go to 0, 1, 0. So now if I complete this to a parallelepiped, but in this case it's rectangular, we get this kind of beautiful shape. And now if we look at what those lengths are, in the x direction we were length 1, in the y direction we were length 5, and in the z direction we were length 1. So our total volume here is 5. Therefore, the determinant of this Q1 matrix is 5. So in other words, if we apply this row operation to a matrix, we have altered the determinant by a factor of 5. The second kind of row operation we had was swapping some rows. So for example, maybe we'll swap the second and third row of a matrix, which I'll denote like this. And if we want to write down the matrix we multiply by to do this, once again, we'll do the row operations to the identity matrix. So we'll leave the first row of the identity matrix alone, and then we'll swap the second and third rows. So I put the third row in the second row, and vice versa. Once again, we want to think about what's happening geometrically. I'm going to use some different colors here to help us out. So our first column here I'll do in red. So our first basis vector 1, 0, 0, that stays at 1, 0, 0. Our second basis vector, which used to be 0, 1, 0, is now 0, 0, 1. So that's in the z direction. It's going up here. And finally, our third basis vector is now just going in the y direction. And so if we complete this, we see that we get a cube here. So our volume is going to be 1 times 1 times 1, which is still 1. However, the determinant is not going to be 1. Remember, our determinant is actually a signed volume, not just a volume. And what the sign is telling us is if we have a left-handed or a right-handed coordinate system. And in this case, what we've done is we've actually changed the handedness of our coordinate system by swapping those two rows. So here we have our basis vectors in order. So we had red first, and then blue, and then green. So in a right-handed coordinate system, if we do the right-hand rule on the red and the blue, we should end up with the positive green direction. But here we see if we curl our fingers from the red to the blue with our right hand, our thumb will be pointing off to the left, which is the negative green direction. So therefore, we've changed our handedness here, so our determinant of Q2 is actually negative 1. And in general, what will happen here is if you swap any pair of rows, that will alter the determinant by one negative sign. So if you do a whole bunch of swaps, you just have to count as you do an even number or an odd number to determine if the determinant is positive 1 or negative 1. The last kind of row operation we have was a kind of shearing operation. So we might add a multiple of one row to another row. So here I've written down we're going to add 2 row 2s to row 3. So with matrix multiplication, we would multiply on the left by the following matrix. We leave row 1 and row 2 alone, but we're going to add 2 row 2s to row 3 here. And I'll attempt to draw this picture. It is not quite as easy to draw as the other ones, but I'll do my best. So our first basis vector, still 1, 0, 0. Our second one is actually changing, and our third one is the same. So our third one is going up here, 0, 0, 1. And then our second basis vector is going 1 in the y direction and 2 in the z direction. So we're going up this way. Let's see, I drew that one incorrectly because that only went up 1 in the y direction, 1 in the z direction, sorry. So let's draw that again to go up. Two in the z direction. All right, so now we'll complete this over to a parallelepiped. So we could go up one further and out this way, back down. All right, so this picture is a little bit messy, but maybe what I'm seeing here is that in the xz plane we have a unit square, so that we can think about that as our base. So that unit square is coming from the x and the z here. And then we have another unit square over for the top over here. So the left side and the right side of our figure are unit squares, which we can treat as our base. And then we multiply that by the height. In this case, our height is going left to right. So we have 1 for the area of our unit square. Our height is that distance 1 to the right. So our volume here is just 1. So our determinant of this matrix is 1. And this is going to hold for any kind of a shearing operation like this, where you're just taking the unit cube and sheared it. In this case, we sheared it up a little bit in the z direction.